Hello and welcome to Assembly Basics 1. So you can see I've already written a little bit here. Basically the topic to begin with this series is going to be Boolean algebra, and then we're going to move on to actual assembly code. Now what you can see is that basically, say we've got three variables here. In this case we're going to have, so n will be 3 here. The number of tuples we're going to have is going to be 2 to the n. So we're going to have 8. So in this case we've got 3. So we're going to have, there's going to be 8. There's going to be 8 tuples, and then we've got this Boolean function on the right hand side there. Well, it should be lowercase, but it doesn't matter. And that's going to have the function which is going to do something with these variables here. And so yeah, and you can sort of imagine that whatever this function is going to this function is going to have an effect on the variables. So obviously, yeah, and of course, like I've done with truth tables before, in this case it would be, for instance, you would have 0, 0, 0, and then you would have 0, 0, 1. And it'd all be in the box, and then you would get the Boolean function, and you would calculate what the answer would be based on whatever this function told us to do. So yeah, so if you've got a number of tuples, so if the tuples are, say, v sub 1, well, I'll put v sub 2, up to vn, then the function is going to be over. It's going to be the whole. It's going to be the whole lot, basically. I want to put v sub 2 in there. At least, because yeah, I mean, I don't think maybe that's not. I guess that's not necessarily the way to do it in computers. But of course, in maths, you would want to at least know which way it's going. Otherwise, you couldn't really infer much about v sub n. So yeah, so we do the function. I'm going to do that over all the different variables here. All right, so yeah, so let's now all right, so kind of a rule here is going to be something kind of yeah, one of the most important things to notice here is how the mathematical functions are kind of converted into the computer functions. So that's x times y. Sometimes you write xy as well. If you write in an equation, you just write xy. Well, depending on what the thing was. So this means x and y. Okay, so times equals and. Okay, so multiplication is an and. Obviously, you don't look at it like that, but yeah. So x plus y, and we can't really do much else with that, is so this means x or y. Okay. And another thing to mention here, the primitive logic gate is a NAND. So that's just, you know, that's just a kind of a fact. Okay, so I'm using new pen here, so I'm trying to keep things clear. And obviously I'm using Paint.net as well, which I haven't used before. Well, I mean, I have used it before, but I just haven't used it for a video. All right. Okay, so now what we want to do is we're going to take a function and we're actually going to use what we just spoke about up here, and we're going to try to get it, try and get some results out of it. All right, so the function is going to be this. So we're going to take these three, like we spoke about earlier, and yeah, and we're going to look at. So this is going to be x plus y, so x or y, and then we're going to times that by z with a little bar on top, and the bar means not. So it's going to be x or so x plus y, which is x or y, and then and not z. So this is the same as x or y and not z. So yeah, it's already starting off quite hard actually, but assembly is quite hard. So we'll see how we go anyway. All right, so let's just try and I guess let's just try and work it out. See if we can do it. We'll leave that there for now. I probably will run out of room, but hopefully by the time I run out of room, maybe I'll. So we're going to put x, y, z. Wow, it's not. And this is going to be f x y z. Okay. All right. So let's start with the first one. See if we can get this. Naught, naught, naught. All right. X or y. Well, they're both false, aren't they? So x or y, that's gonna be 0. So x plus y is going to be 0, 0, and then not z is going to be 1. So 0 and 1. For an AND gate, you need to have both true. So that's going to be 0. So yeah. All right. Let's just keep on going. See if we can get this. So x or y, so 0 or 0 is going to be 0. It's going to evaluate to 0. 0 and 0 is going to be 0. Okay. So x or y, so 0 or 1 can be true, can be 1. So that's going to be 1. 1 and not and 1 and 1 are both true, so it's 1. All right. So 0, 1, 1 now. Now, okay. So x or y, so 0 or 1 is 1. 1 and 0 is 0. All right. So what I want to do, yeah, okay, we're actually going to, I'm going to do the whole lot, I think. It makes sense here, doesn't it? Okay, so I kind of, at this point, I'm going to just try and remember it. All right. So 1 or 0 is 1. 1 and 1 is 1. Okay. So 1 or 0 is 1. And 0 is 0. Okay, and just move down a bit. All right. So 1 or 1 is 1, and 1 is 1. I guess I could say it differently. I could say 1 or 1 is 1, and not 0, which is 1, and the 1 is 1. Yeah. I'm going to do a little bit more in the way of maths here with this. I've actually got some room on the right hand side, so maybe I'll just do a bit of maths here. All right, let's just finish this off then. 1 or 1 is 1, and 1 and 0 is 0. 1 and not 1 is. All right, so you can see that for this, expression. So yes, this is an important thing to notice. This is an expression. So you can't. Yeah, well, I suppose it's. I mean, a lot of stuff's an expression. Expression. Boolean expression. All right. All right. So yeah, like I say, I'm gonna move through this quite slowly. There is something else I want to think about. But I'm not going to do that at the moment. I'm just gonna think about what I've done here. So yeah, so we can. Let's just think about a way we can actually get this. So we do naught and naught times that's the thing. Can I do it like that? I wonder if I can just do it like this. Let me try the next row. All right. So that one worked all right. Now let's try this one. So yeah. So the first one is basically saying 0 times 1 is 0. The next one is saying 0 times 0 is 0. But is it actually going to work though if I just do it like this? It's weird to think of this addition. Yeah, you can just write it like that. Yeah, you can. You can just do it like that. Because look, because 0 times 1, 0 times 1 is 0. 0 times 0 is 0. 1 times 1 is 1. It's pretty cool actually when you think about it. Yeah, so that's pretty cool. And should I just do the whole lot? Fuck it, I'll do the whole lot. So 0, 0, 0. 0, 0, 1, 0. So yeah, so then it would be 0, 1, 1. And we put the bar in here, even though it's not actually in the table. So that's 1 times 0 is 0. So after 0, 1, 1 is going to be 1 plus 0. And put that in there. So that's 1 times 1, which is 1. And then we're going to do 1, 0, 1. So 1. So that's going to be 1 times 0, which is 0. 101, so we've got 2 left, don't we? Yep. We'll just do those then. 1 plus 1, and then do not 0 here. So so 1 or 1 is 1. 1 and not 0, so it's 1 and 1 is 1. Finally, one or one is 1 and 0. 1 and 0 is 0. So if we look at the right hand column there, I've actually done exactly the same thing. So it's 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0. So yeah, so I've written it out in these different forms like that. All right, so maybe actually I can, maybe actually I will just go a little bit further here. And we're going to talk about canonical representation. Okay. So yeah, that actually worked out with less hiccups. I suppose I have done a few things with this before, so well, I mean, yeah. Okay. Okay, so let's think about these steps we need to take here. So I'm just going to try to go through these steps because I'm not quite sure what's going on with this. Focus. So I'm just going to write a step, and then I'm actually going to do the step. Focus on all rows. That should be okay. So where the function, I'll just you know, as a value 1. Okay. All right. Well, All right, so it's going to be the third row, isn't it? 0, 1, 0 is going to be 1. 1, 0, 0 is 1. And 1, 1, 0 is 1. Okay. Yeah. All right. Well, done that, I suppose. I haven't really done it, but okay. So now it gets a bit more complicated. Like I say, I didn't really. Well, we'll see. We'll see. I'm just gonna try it. It's not that much here. Yeah. For each row, to be honest, I've done this fucking millions of times. So this I've done much harder stuff than this before. For each row, this is ridiculously basic. You know, so it almost sounds stupid even commenting on it really. So for each row, we construct a term, but at the same time, I find it incredibly difficult. We construct a term created by handing together literals. I've only actually really used that term when I thought about Java strings. So I don't know if that's anything to do with it. It probably is, but it was anyway. I'm not going to focus on that. I don't want to focus on Java at all, really. And together literals. So literal, and that's defined as variables or their negations. It's funny because when you put the truth table down, it looks like you're just putting down. It feels like constants that you're putting down, but they are actually variables x, y, and z. All right. Um, oh, actually, this is actually much simpler than I thought it was. I was getting a bit confused, but all right. So in the third row, the third row is 0, 1, 0. Zero, 1, 0. Okay. And we know that is going to and that's going to and that is going to and we've said before the function is going to be 1. All right. So what we could say here I see, yeah. So basically, what we can say is we can use a not gate, basically. Oh. Where's the... Oh. Sorry, this must be a ridiculous sounding video. All right, yeah. It's because I'm actually not saying what I'm thinking at the moment. Basically, right. It goes back to what I said at the beginning. When you have say x, y, z like this, This is like this is and. It's obviously multiplication, right? I'm not going to put that here. It's obviously multiplication, and that's an and. When you have x plus y, that's or. And when you have not x, that's not. When you have the bar over the x, that's not. And the idea with this is that we can express that entire truth table. We can express that entire truth table in a very in this thing called the canonical representation. So yeah, and I'll write the conclusion at the end. I'm, as you would. All right. So what this means, right, is that for this row, for instance, we can write this as so if we look at what this is, right, this is basically the same as this. Like that. That's what that is. All right, so let's now look at the other rows then. All right. All right, let me write this a bit differently now. All right, so we're going to put. All right, you know what? I'm just going to. Actually, I know how I'm going to do this. So what are the other rows where we had 1? So we had that one, which is the 0101 was 1. And the next row we've got is the 100 and the 110. They're the only 3. Right? Yeah, the 100 and the 110. And yeah, okay. So what we can say now is we want this to get the canonical representation. What we're going to need to do is we want to get all the true values. So we're going to use or. So you can see already we've used and, ors, or nots, and every Boolean function can be expressed like this. So we've got it's kind of hidden, the multiplication, but that is and. This is not x and y and not z. And then we have an or. So you can see I've said not or and. And then all we do is so the next bit it's going to be x not y not z. And then the next bit is 110. So we'll put that in. 1 1 0. So x, y, and not z. And this, so this is the canonical representation. Every Boolean function can be expressed like this, using only these 3 Boolean operators. Can be expressed using these 3 Boolean operators. Okay. So yeah, so that's pretty That's pretty. That's pretty cool. I'm already thinking about something else about how this relates to the original thing that we spoke about. Hmm. But I probably shouldn't think about that. All right, that's it. Thanks for watching.